In image classification, the goal is to categorize images. The example illustrates a scenario where the machine learning problem is to classify images into two categories: cats and dogs. Sentiment analysis involves determining the emotional tone of a piece of text. In this example, the model needs to classify text reviews as positive, negative, or neutral, reflecting the sentiment expressed in the text. Model selection is about choosing the appropriate algorithm for the task. Logistic regression is a linear model for binary classification. Neural networks are more complex models capable of learning nonlinear relationships. Specifying the architecture involves defining the number of layers, neurons per layer, and activation functions. Problem definition involves clearly articulating the task the machine learning model will solve. Image classification is about assigning a label to an image. Sentiment analysis is about determining the emotional tone of text. This refers to the initial step of clearly articulating the machine learning problem. This refers to the process of selecting a suitable metric to evaluate the performance of the chosen machine learning model. This step details the construction of a model designed to predict when the primary model will make errors. This error predictor employs Bayesian methods to quantify the uncertainty in its predictions. The goal is to identify which features are most indicative of potential errors in the main model's performance. Prepare the dataset for training the error predictor by including the original model's training data, error features, and binary error labels which indicate whether the original model correctly classified each instance, with 0 representing a correct classification and 1 representing an incorrect classification. This refers to the dataset used to train the initial machine learning model that is being analyzed. These are the features engineered to represent the hypotheses about the causes of errors. For example, blurriness score for images or sentence length for text. These labels indicate whether the original model correctly, 0, or incorrectly, 1, classified each instance in the dataset. This forms the target variable for the error predictor model. The training data, error features, and binary error labels are combined into a single dataset. This dataset is used to train the Bayesian error predictor. Select a Bayesian model suitable for predicting errors. This is a Bayesian approach to logistic regression, suitable for binary classification problems like predicting errors. It places prior distributions on the model's weights. This type of neural network uses Bayesian inference, providing uncertainty estimation in its predictions, which can be valuable for assessing the confidence in error predictions. This is a non-parametric Bayesian model useful for classification, especially when dealing with complex, nonlinear relationships between features and error patterns. This involves specifying prior distributions for the parameters of the chosen Bayesian model. For example, assigning weakly informative priors to error features, indicating an initial assumption that no single feature is overwhelmingly important. Training the Bayesian model involves inferring the posterior distribution over the model's parameters using techniques like Markov chain Monte Carlo, MCMC, particularly Hamiltonian Monte Carlo. The trained Bayesian error predictor outputs a probability that the original model will make an error on a given instance. This probability reflects the confidence that the original model will be wrong, given the instance's features and the prior beliefs. Now, let's create a model, the error predictor, using a Bayesian approach to predict when the original model is likely to make mistakes. Prepare the dataset for training the error predictor. This involves using the same instances from the original model, along with the created error features, and a binary label, indicating if the original model's classification was correct or incorrect. One option for the error predictor is Bayesian logistic regression. This is a common choice for binary classification problems where the goal is to predict a binary outcome, in this case, whether the original model makes an error or not. The model's weights have prior distributions, representing initial beliefs about feature importance. The trained Bayesian error predictor outputs a probability indicating how likely the original model is to make an error on a given instance. This reflects the model's confidence that the original model will be wrong, given the instance's features and prior beliefs. Priors are specified for the parameters of the Bayesian model. These priors represent the initial beliefs about the importance of the error features before seeing the data. Train the Bayesian model using the prepared dataset. This involves inferring the posterior distribution over the model's parameters, given the data and the priors. Markov chain Monte Carlo, abbreviated as MCMC, methods, such as Hamiltonian Monte Carlo, abbreviated as HMC, are often used for inference in Bayesian models. These methods help to estimate the posterior distribution, especially when it is difficult to calculate directly. After training, we obtain the posterior distribution of the model's parameters. This distribution represents the updated beliefs about the parameters after considering the observed data. A Gaussian process classifier can be another good choice, especially when dealing with complex relationships. A Bayesian neural network provides uncertainty estimation, which is useful in this step. A binary label, either 0 or 1, is added to each instance, indicating whether the original model classified it correctly, 0, or incorrectly, 1. Error features, which represent hypotheses about error sources, are included. The dataset for the error predictor consists of instances used to train the original model. It also includes the newly created error features like blurriness score or sentence length, and a binary label indicating whether the original model correctly classified each instance. A value of 0 indicates a correct classification and a value of 1 indicates an incorrect classification. Selecting the appropriate Bayesian model for predicting errors. Options include Bayesian logistic regression, Bayesian neural networks, and Gaussian process classifiers. The choice depends on the complexity and nature of relationships between error features and errors. Assign prior distributions to the parameters of the Bayesian model. These priors represent initial beliefs about the importance of error features before observing the data. A weakly informative prior may be assigned, reflecting an initial assumption that no single feature is overwhelmingly important. Training the Bayesian model using the prepared dataset. This involves inferring the posterior distribution over the model's parameters, given the data and the priors. Markov chain Monte Carlo, abbreviated as MCMC, methods, e.g., Hamiltonian Monte Carlo, are often used for inference in Bayesian models. The trained Bayesian error predictor outputs a probability that the original model will make an error on each instance. This probability reflects the model's confidence in its prediction of error based on instance features and prior beliefs. Bayesian logistic regression, a common choice for binary classification where the error label is the target variable. The weights have prior distributions. Bayesian neural network. This provides uncertainty estimation, which is useful in error prediction to quantify the confidence in predictions of errors. Gaussian process classifier. A good choice particularly when dealing with complex relationships between error features and errors made by the original model. Analyzing the posterior distribution of the Bayesian error predictor's parameters. This reveals which error features are most strongly associated with the original model's mistakes. Error features are computable characteristics of the input data designed to capture patterns in the original model's errors, like a blurriness score for images or sentence length for text. Binary labels indicating whether the baseline model made a correct prediction, denoted by 0, or an incorrect prediction, denoted by 1. The instances used to train the error predictor are the same as those used to train the original model. This ensures the error predictor learns to identify errors on data the original model is familiar with. The Bayesian error predictor outputs a probability for each instance, representing the likelihood of the original model making an error. This probability quantifies the confidence in predicting the original model's mistakes. Combining the original model training data, the computed error features, and the binary error labels to create a dataset specifically for training the error predictor. This combines both the data and identified weaknesses. The goal is to create a new model, called the error predictor, to predict when the baseline model will make mistakes. This model will be Bayesian, allowing quantifying uncertainty. Prepare the dataset for the error predictor, using the same instances as the original model. Add error features and a binary label, 0 for correct classifications, 1 for incorrect. This labeled dataset is essential for training the error predictor. Select a Bayesian model suitable for binary classification. Options include Bayesian logistic regression, Bayesian neural networks, and Gaussian process classifiers. The choice depends on the complexity and relationships expected in the data. Specify prior distributions for the model's parameters. These priors represent initial beliefs about the importance of error features before seeing the data. Weakly informative priors are often used, reflecting an initial assumption that no single feature is overwhelmingly important. Train the Bayesian model with the prepared dataset. This involves inferring the posterior distribution over the model's parameters, given the data and the priors. Markov chain Monte Carlo, MCMC, methods, such as Hamiltonian Monte Carlo, are frequently used for this inference. The trained Bayesian error predictor outputs the probability that the original model will err on each instance. This probability reflects the model's confidence in its error prediction, based on the instance's features and the prior beliefs. A common choice for the error predictor because the error label is a binary target variable and assigns prior distributions to weights. The Bayesian neural network provides uncertainty estimation, which is very useful in this context. It is one of the options for the error predictor. Gaussian process classifier, another option for error predictor, deals with complex relationships. The coefficients of error features are assigned a prior that reflects belief that no single feature is overwhelmingly important. Prior probability distribution represents subjective beliefs about a parameter before evidence is considered. The Bayesian error predictor predicts the probability that the original model will make an error on each instance. The probability that the original model will be wrong, given the instance's features and initial beliefs. Markov chain Monte Carlo, with example of Hamiltonian Monte Carlo, are a class of algorithms for sampling from a probability distribution. The error predictor is trained using a dataset which includes the same data used for the original model, error features quantifying potential error sources, and binary labels denoting correct, 0, or incorrect, 1, predictions of the original model. The model requires specific data preparation steps. The same instances used to train the original model are incorporated, along with automatically computed error features, to form a combined dataset used for training error predictor. Select a Bayesian model appropriate for binary classification tasks, like predicting errors. Examples are Bayesian logistic regression, Bayesian neural networks, and Gaussian process classifiers. Bayesian logistic regression is a probabilistic model suitable for binary classification problems, which outputs the probability of an error given some input features. The model incorporates prior beliefs about the parameters through prior distributions. A Bayesian neural network extends the traditional neural network by placing probability distributions over the network's weights. This allows for the estimation of uncertainty, which is valuable in assessing confidence in error predictions. Gaussian process classifier is a non-parametric model that defines a probability distribution over functions. It is useful for capturing complex relationships between error features and prediction errors. Prior distributions represent initial beliefs about the importance of error features before observing any data. Weakly informative priors can be assigned to the coefficients of each error feature. Prior distributions are established for model parameters using weakly informative priors, signifying no single feature is overly important initially. The Bayesian model is trained by inferring the posterior distribution over the model's parameters, given the data and the priors. Markov chain Monte Carlo, abbreviated as MCMC, methods like Hamiltonian Monte Carlo are frequently employed for inference. Markov chain Monte Carlo approximates the posterior distribution by drawing samples from it. Markov chain Monte Carlo, MCMC, is a class of algorithms for sampling from a probability distribution based on constructing a Markov chain that has the desired distribution as its equilibrium distribution. Hamiltonian Monte Carlo is a specific MCMC method that uses Hamiltonian dynamics to more efficiently explore the parameter space. The trained Bayesian error predictor estimates the probability that the original model will make an error on a given instance. The Bayesian error predictor outputs a probability indicating the confidence that the original model will err.